So here we have another section, and this is starred, so you're not going to be examined on this, but it's good that you see it and you should watch this. It'll make you understand relations a little better, and you will need to understand this concept for next semester, so there's no harm seeing it at the moment. Now, we haven't spoken about relations for a little while, but a relation on a relation between A and B is a subset of A cross B, and a relation on A is a subset of A cross A. And what you can do, if A is finite, you can represent relations by a digraph. And what we do is when A1 is related to A2, and another way of writing this, by the way, is saying that A1, A2, now that's an element of A, ordered pair, so it is in the Cartesian product, and or a relation is a subset of that, so this, in this case, we're saying is in the relation. You draw an arrow between A1 and A2. So for example, we could have a relation on ABC, and what we do is we represent the elements as nodes. So nodes, we'll see a little bit more when we do graph theory. Say A, B, C. So it's just like a little network. And we connect them if they're related to each other. So for example, A is related to A, so we send an arrow from A to A. So that'll just be a little loop. A is related to B, so we put an arrow from A to B. Now this part of the things, drawing this digraph for relation, will be coming up later on. It's the properties later on are reflexive and symmetric and transitive. That's the thing that is not going to be examined. Now the other one, we've got B related to B, so there'll be a loop at B. And finally we have C is related to B. And finally we have C is related to A. So that is the digraph of this relation. And notice this is not all possible pairs of a Cartesian product A, for example. CC is not in there. And that's what a relation is, a subset of the full Cartesian product. Here you've only got 4 of them. I think there's actually, the full Cartesian product will be 9. We're just taking these 1, 2, 3, 4, 5, excuse me. And this is the digraph of it. Okay. Now we have 3 properties of relations that we're interested in particular. The first is when every element is connected to itself, or probably that should really say related to itself. And that means in the digraph, there'll be a loop. So basically, every single element in the set A will always have A related to A. And if it has this property, then it's said to be reflexive. So for example, this relation above is not reflexive because C is not related to C. Now we'll have a little look at a relation here. We'll say A is related to B if A divided by B is a natural number on this set. So let's see, we'll draw, maybe we'll just do the ordered pairs first. So the ordered pairs is 1 is related to 1 because 1 divided by 1 is a natural number, equal 1. 1 is not related to 2 because a half is not a natural number. 1 is not related to 3, 1 is not related to 4. 2 is related to 1 because 2 over 1 is 2 is a natural number, so 2 is related to 1. And also 2 is related to 2 because 2 divided by 2 is a natural number. So this is in the relation. Let's see what else we have. Is 3 related to 1? Yes, it is, because 3 divided by 1 is a natural number. 3 is related to 1. 3 is not related to 2 because 3 over 2 is not a natural number, and 3 over 3 is a natural number, so 3 is related to 3. And finally, 3 is not related to 4 because 3 over 4 is not a natural number. And the last one, you have 4 is related to 1
because 4 over 1 is equal to 4 as a natural number. 4 is related to 2, because 4 over 2 is a natural number, it's equal to 2. And finally 4 over 4 is equal to 1 is a natural number, so 4 is related to itself. So this is the full relation. Now remember, again, the relation is a subset, a relation of S is a subset of S cross S. S cross S has got 16 elements, so if you take 0 to 16 of them, that is a relation. And this is a particular relation here. And we'll draw the diagram for it. So we have 1, element 1, element 2, element 3, and element 4. And remember, we connect nodes A to B if A is related to B. So 1 is related to 1, so we'll draw just a loop. 2 is related to 1, so draw an arrow between them. 2 is related to 2, and 3 is related to 1, 3 is related to 3, 4 is related to 1, 4 is related to 2, and finally 4 is related to 4. Now every single element in S is related to itself. 1 is related to 1, 2 is related to 2, 3 is related to 3, 4 is related to 4. Equivalently, in the diagram, there's a loop at every node. This is a reflexive relation. And that's one of these properties you're going to learn about next semester. Now, the next property we're going to look at is symmetric. Now there's an inherent asymmetry in it, in that, for example, 4 is related to 1, but 1 is not related to 4. You've got an asymmetry, a breakdown in symmetry. If you don't ever have that, if whenever 4 is related to 1, 1 is also related to 4, then the relation is said to be symmetric. So we can write that, something like that. Whenever A is related to B, B will also be related to A. Now if A is not related to B, B will not be related to A either. So that either nodes are unconnected, they're not related at all, or there's a double edge. A to B and B to A. And if you have this property, then R is said to be symmetric. Now neither of the previous two are symmetric. If we look at the first, we have, for example, that A is related to B, but B is not related to A, so it's not symmetric. And here, we already spoke about 4 is related to 1, but 1 is not related to 4. So neither of those are symmetric. Now, here we've got one that is symmetric. An example of a symmetric relation is siblinghood. So I am a sibling of, in other words, I'm a brother or sister. So if you take any set of people, for example, mother, father, child 1, child 2, and say that the two people are related if P1 and P2 are siblings. Now, obviously, the mother shouldn't and the father shouldn't be siblings of each other or of the children, right? We'll just assume it's just a kind of a what you'd normally say, maybe a normal situation. Let's see what we got. So we have a father. We've got a mother. And we've got 2 children. Child 1 and child 2. Now, as I said, we hope the father is not a sibling of the mother. That would be, that's illegal. The mother is not a sibling of the child. Again, just, we won't go there. The only siblings here are child 1 is a sibling of child 2. And child 2 is a sibling of child 1. So this is a completely symmetric situation. Now, the only symmetry is that when you have one edge, from there you have one going back. This is not reflexive. We'll say that we can say, I mean, are you your own brother? We'll just say no. So we'll say that any person is not a sibling of themselves. Now, you could make that argument, but I won't do that. Now, the next one is a bit harder. It's what's called a transitive relation. And if A is related to B and B is related to C, then A is also related to C. When you have that property, that's transitive. So again, we'll look at an example. In this case, whenever a pair of arrows goes from A to B to C, we'll also have A to C. Siblinghood is transitive. Now you can't really see it here, but if you have more than 3 children, for example, I've got 2 brothers and 2 sisters, and I am a brother of my brother, I'm a sibling of my brother is a sibling of my sister, and therefore I am a sibling of my sister. That's what transitive looks like. We'll look at another example. A good one is less than. So A is related to B if A is less than B. So if we look at, say, 1, 2, 3, and 4. So 1 is less than 2, so 1 is related to 2. 1 is less than 4, so I connect them. 1 is less than 3, so I connect them. 2 is less than 3, and 2 is less than 4. 2 is not less than 2, of course. 2 is not less than 1. 3 is less than 4, and 4 is not less than anything. And this is transitive. 1 is less than 2, and 2 is less than 3, so 1 is less than 3. Or I can say 1 is less than 3, and 3 is less than 4, so 1 is less than 4. Basically what you have is whenever you've got 2 arrows, the triangle will be completed. So here you have, can we see 2 arrows? They have to be in a line. So say boom, boom, completed. Something like this. This one is not reflexive, 4 is not less than 4, and it's not symmetric. 1 is less than 3, 3 is not less than 1. And basically what you have is relations that are reflexive, symmetric, and transitive are said to be equivalence relations because they resemble equality. They look like equality. So I think if I think carefully, have I got one? Yeah. We can say that it's basically, so your equals will be like this. Everything is equal to itself. That's obvious. And then the second thing is, if I am equal to that chair, then that chair is also equal to me. And the last thing is, if I'm equal to the chair and the chair is equal to the window, then I am also equal to the window. So it models equality. And it's where you get other equivalencies. For example, one of them like this. So we've got a relation on the real numbers, so all possible real numbers, and we say that x is related to y. Another way of writing this is xy is in the relation if the absolute value of x is equal to the absolute value of y. And what this is saying is that x is related to y if their distance to 0 is the same, actually. And so, if we look at this, it's reflexive. The absolute value of, say, 2 is equal to the absolute value of 2. Symmetric. If the absolute value of 2 is equal to the absolute value of 2, or minus 2, then it works both ways. And it is transitive as well. So basically, you've got this kind of, well, they're the same up to equivalence. So, like 2 and minus 2 is equivalent under this relation.